Today we're going to talk about lifting line theory and build on some ideas that we started discussing with related to wings. At the end of last time, we had built a simple model for a wing. You recall if I had a wing shaped like this, that we used what was called the horseshoe vortex to model the wing. And based on the Helmholtz vortex theorems, we know this needs to actually be closed, but in practice, we extend these trailing vortices infinitely far away. So we generally don't draw it and just consider this horseshoe shape as a representation. We also saw that this does seem to match, appears to match some physical experiments, but is insufficient, an insufficient model in matching reality. For example, from the theorems, we know that the circulation gamma must be constant everywhere along that vortex, right? And it's in this direction as shown here, inducing a downwash in between. If we were to draw the lift distribution, so if I looked at, say, a back view of the wing, because gamma here is constant all the way across the wing, that would mean that the lift distribution, the circulation distribution would be a constant line here. Pretend I drew a straight line there. Gamma, we know that that is unphysical, not realistic. For one, the lift distribution must go to 0 at the tips, right here at the wing tips. It can't have this infinite slope as we go to 0. There's no surface here at the tip to support a pressure differential, so it's going to have to go to 0 towards the edges here. We also know it just doesn't look like that kind of a shape. Typically, the lift distribution for just a wing, ignoring fuselage or other interactions, might look something more like this, right? At the very least, we need to go to 0 at the tip. So we could improve our model. One way we could do this is we could just add more horseshoe vortices. And this is consistent with the data. In the experiments that we saw, we did see a concentration of vorticity, but that just means that's where the highest vorticity is. That doesn't mean that's where all of it is. We just can't visualize it all. And the vorticity is really related to the slope of this function here. So we could nest in additional horseshoe vortices, right? And we could just layer them on top. And so this one might have strength gamma 1, this one gamma 2, this one gamma 3. And in a discrete sense, right, if I drew another wing, this is going to create a blocky but somewhat better lift distribution, right, where it looks maybe like as follows. And depending how I define gamma, like let's say this is gamma 1, this would be gamma 1 plus gamma 2, and this would be the sum of all of those gammas 1 through 3. And in the limit, right, if I add an infinite number of these, then I can approach the type of smooth distribution that we want. Okay, so we're going to do 2 things. Next time, or maybe in 2 times, we'll use a model where we kind of build these discrete horseshoe vortices, a numerical model, kind of analogous to what we did with the panel method with the airfoils. But this time we're going to use a method, an analytic method, maybe more analogous to thin airfoil theory, where we can get some solutions, perhaps not as general, perhaps not as versatile, at least in the current form, but it will allow us to get some analytic solutions that will be generally useful. Okay, so this is the type of model that we're going to build, an infinite number of these horseshoe vortices so that we can build a smooth lift distribution. We're going to need to define one parameter, lowercase gamma. This is essentially the vorticity. It's the derivative of the circulation with respect to y. Y is the distance out the side of the wing, remember? So it's basically, you could think of it as the vortex strength per unit length, right? Very similar to things we've done before. So it's a strength per unit length. All right, so with that in mind, we want to analyze some arbitrary point. So here is, for example, one infinitesimal segment of vorticity, this lowercase gamma, strength per unit length. And there's a continuous sheet now of this vorticity. We're just taking one little line segment at some arbitrary point, y prime. So gamma is a function of y prime. That means it's varying continuously along this flat wing surface. This one infinitesimal segment has some circulation associated with it. And so at some other arbitrary location, some distance y from the center, it's going to induce a velocity, some velocity w, or infinitesimal velocity dw, which is now a function of y because it's varying also along the wing. So just from things that we derived before, this is now a semi-infinite vortex. And remember, a semi-infinite vortex has a strength of gamma, or sorry, induces a velocity of magnitude gamma over 4 pi r. So we can say that this infinitesimal velocity is gamma, which is lowercase gamma times its length, right? Because this is strength per unit length times the length. That gives me gamma. This is basically d gamma, right? If I multiply this times this, it gives me d gamma. Gamma over 4 pi r. So I've got 4 pi, and r in this case is this distance, right, from the center of the vortex to the point I'm evaluating at. So it's y minus y prime. Okay, that is my infinitesimal strength. And I've got to be a little careful on the signs here. So gamma in this case is actually negative because remember, gamma is the derivative of gamma with respect to y. And as I'm on the right side of the wing in this picture, I'm moving out to the right, so y is increasing. But as I move out this way, capital gamma is decreasing. So this whole term is negative. However, the velocity that's being induced is in the upward direction, positive. So I'm going to put a minus sign here. Okay, that's the infinitesimal one, but I need to integrate over this entire vortex sheet, right? There's an infinite number of these vortices where gamma is again varying as a function of y. So I need to integrate across the entire wing. So the induced velocity as a function of y is then I'm pulling out the 1 over 4 pi out of the integral. I need to integrate across the wing, gamma, and I'm just going to write explicitly, it's a function of y prime. That's not a multiply, that's just a function divided by y minus y prime. Okay, and I integrate along the wing, so that's from minus b over 2 to b over 2. Remember, b is the variable that's used for span. Okay, now that we have can compute the velocity, this downwash anywhere, we can compute the induced angle of attack. Remember that normally, if there was just a 2D wing, all I'd have is my free stream velocity. But because I've got vorticity being generated on the wing in this 3-dimensional space, I get downwash. That's what this induced velocity is. And that's, as drawn in the picture, downward. We've calculated generically upward, so I'm gonna have to make sure to change the sign here. But I can now calculate this induced angle of attack, how much my angle of attack is reduced by the presence of this downwash, and it is the arctangent of a minus w over v infinity. And I need the minus sign here because I've defined this angle here as a positive here down, whereas I computed it positive up before. So if I put all that together, I now have my induced angle of attack is the arctangent of this whole thing, which is this integral 1 over 4 pi, putting in the v infinity from the denominator, integrate minus b over 2 to b over 2, gamma, which is a function of y prime, dy prime over y minus y prime. All right, so a little bit ugly, but we've got it. Okay, so the next thing, now that we have that angle of attack, remember we already could before, if I knew my velocity, and I've got, well, let's just say for an airfoil, actually, let me just draw it this way. No, that's fine. I'll just draw like that. Here's the chord line. Here's v infinity. Here's my angle of attack. We already found from thin airfoil theory that my lift coefficient is 2 pi times alpha minus alpha 0. We got this very useful result, but we found that for a 3-dimensional case now, each airfoil section, we could still use that theory. However, we have to reduce my angle of attack by this induced angle of attack because of the presence of the downwash, right? Because there's now downward velocity, I've reduced my angle by exactly the amount that we just calculated. And to make this more general, I'm going to replace this 2 pi with m. Again, it's 2 pi, that's the thin airfoil theory, theoretical limit. In general, this equation still applies, although the slope is usually maybe slightly less than 2 pi. So we'll just use m to indicate that slope, though it's generally very close to 2 pi. All right, so from Kajkowski theorem, I can relate my lift to my circulation. So I'm going to do that. This is my Kajkowski theorem, just in terms of magnitude. And by definition of what the CL is, lift coefficient, it's as follows. So if I solve this for CL, I'm just trying to get an expression in terms of circulation, because all my expressions here in terms of derivative circulation, I just want to get everything in terms of the same equations. This tells me that CL is equal to, let's see, these rows will cancel, one of the V infinities will cancel, 2 gamma over V infinity times C. Okay, so I'm going to plug that in to here, and I'm going to plug my expression for the induced angle of attack on the last page into here. And so now I get this big long expression, and I'm going to explicitly write that gamma here is a function of y. I'm just writing this term out. V in general could be a function of y. C, certainly a function of y. The chord length varies along the wing. The lift curve slope could potentially vary along the wing. I'm now writing these terms. Angle of attack varies. Zero lift angle of attack varies. And now I've got to copy that expression from the last page. It's the arctangent of 1 over 4 pi. V is a function of y. Integrate across the span. And I've got gamma, which is varying along this dummy variable, y prime, dy prime, all over y minus y prime, and then close my parentheses here. All right, so this big long equation, this is called the fundamental equation, or the fundamental equation of lifting line theory. Okay, so it's kind of big and ugly, but it really only uses a couple basic principles. One is just this result from thin airfoil theory that we've reduced by the induced angle of attack. And the induced angle of attack we calculated by this vortex sheet, right? We just integrate across the sheet, figuring out how much velocity would be induced by having an infinitesimal or infinite number of these vortex filaments that have infinitesimal strength. Okay, so put all that together, we have an integral that potentially we could solve, right? If I knew I have a given wing, right, with given airfoils. So if I have a given wing with given airfoils and given conditions, I know the shape of the wing, the chord distribution. The airfoil data tells me my lift curve slope and zero lift angle of attack. From the free stream properties, I know my velocities and angle of attack, right? And so I could potentially solve it given, right, geometry and conditions. I could solve for a gamma, and this is the derivative gamma. So those are really my only unknowns, is trying to figure out what that circulation distribution is. I'm figuring out what the lift distribution on the wing is from the geometry. Though, it's potentially difficult to solve. I've got an integral, I've got derivatives and so on, and arctangents. So we're going to start with we're going to kind of work backwards. We're going to assume a shape for the lift distribution, work out what happens in the equation, and then we'll work out a more general case, somewhat similar to what we did with thin airfoil theory, where we started with the symmetric airfoil and then went to a cambered case that was more general. So we're going to start with a lift distribution. So rather than solve the equation, we're going to put in a solution. We're going to assume that our lift distribution is elliptical. We'll see why that's a good choice later. So we're going to assume that my circulation is elliptical, and what that means is that this is literally just the equation of an ellipse. So it'll look like this: P over 2 squared. So in other words, if I was plotting the lift distribution along the wing, this shape is the shape of an ellipse, and that's shown here. This is the equation of the ellipse. So this tells me the shape. Gamma 0 tells me the magnitude. That's just what is the circulation here at the center. So I can have many ellipses of different magnitudes. They're all ellipses. I just am free to choose this parameter based on how much lift I have. From the previous equation, we'd also want little gamma, right? Which, remember, is d gamma dy. I can take that derivative. I'm just going to do it in one step here. Make sure to do the chain rule. It gives me minus gamma 0 4 y over b squared times 1 over the square root of all that stuff, 1 minus 2y over b squared. Okay, so that's the derivative. We're going to do the exact same trick that we did in thin airfoil theory, and we're going to do a coordinate transformation, and we'll do the same one basically as the coordinate transformation. We're going to do y equals b over 2 times cosine theta. And remember that my integral goes from minus b over 2 to b over 2. So we can see now with this transformation, that means I want cosine of theta to go from -1 to 1. which means that theta must go from pi to 0. Oops, that should be 0, right? Because if I plug in pi here, this gives me minus b over 2. Plug in 0, that gives me plus b over 2. So I'm going to integrate from pi to 0. Now, if I make the substitution, right, if I plug in y here is b over 2 over cosine theta, you can see the b over 2's will cancel. I'm going to get a cosine squared. 1 minus cosine squared is sine squared. The square root of that is sine theta. So gamma in these new coordinate system is just going to be gamma 0 times sine theta. So that's going to simplify quite a bit. This expression is also going to simplify. I'm going to just show you all that on the next slide here. So I'm going to plug all these things in, gamma and gamma, and I'm only going to plug it in for just this term for now. Actually this term, the downwash. We're just going to take it a step at a time. So just plugging it in, I'm just skipping the tiny bit of algebra here. What we get is that the downwash is in this coordinate transform space, 2 pi over b. And remember, my integral now goes from pi to 0. I get integral from pi to 0. That's integrating along the wing. And I get cosine of theta prime over cosine theta minus cos theta prime, d theta prime. And these primes occur because if you'll recall in the downwash function here, right, I've got y primes and I've got y. So I had to make two substitutions, one in terms of a theta and one in terms of a theta prime. Simplify it, simplifies quite nicely. And so we're actually going to use the exact same integral that we had from thin air flow theory. That was this one. You might recall that we used it twice in the cut it condition here. But in our case, it's simpler here. If we compare this with this one, let's just look at the n equals 1 case, because that's all we need. That says the integral from 0 to pi of cos phi over cos phi minus cos theta d phi equals, if I put n equals 1 here, these cancel and I get just pi. So if we compare this integral with ours, it's very similar, though not exactly the same. We notice that the integrand d phi, it's in the numerator, so that matches, but this term and this term are switched from these. So if I multiply this by a negative sign, then I could switch these to match this one. However, the integration limits are also flipped. So that will create another negative sign. So those cancel out. And in other words, this entire integral is just pi. So we get our first result here that the downwash along the wing is minus gamma 0 over 2b, the pi in this denominator and the pi from this integral canceled out. So here's our first useful result here, is that for an elliptic lift distribution, the downwash is constant along the wing, right? Because this is a function of theta, which again varies from pi to 0, representing the variation along the wing. B is just the wingspan, that's a constant, and gamma 0, remember, is just the magnitude. It's a number, it's a constant, indicating how, or the magnitude of this lift distribution. So this is a constant along the entire wing. So for an elliptic lift distribution, downwash is constant. That'll be important later, but we can continue building off of that. So now that we have downwash, we can, for example, calculate other things. Right, we can calculate our induced angle of attack. The induced angle of attack is the arctangent of minus w over v infinity, which in our case is going to be for an elliptic wing. What is that? The arctangent of gamma 0 over 2b v infinity, right? Did I do that right? Yeah. Okay, so that's nice, but we'd like to change this into variables that are more useful. Span and speed are very useful to us. Those are quantities that we'll naturally have. Gamma 0 is not perhaps less natural, right? That's just what's the magnitude of the circulation distribution. That's not usually a fundamental parameter we talk about as the wing designer, the aircraft designer. Looking at the airplane, we won't necessarily talk about the magnitude of the circulation distribution. So we want to relate this to things like area or lift coefficient, speed, things that we know. So let's again go back to what our lift distribution is. We know what gamma is. It's this. So from the Kajkowski theorem, we know that our lift is just rho v gamma. So as a function of y, it's going to be rho v for this elliptic lift distribution gamma 0 times the square root of 1 minus y over b over 2 squared. So that tells me how my lift distribution varies. Of course, these are just constants, so the lift distribution is elliptic if the circulation distribution is elliptic. And my lift is now just the integral of that lift distribution along the wing. As you might suspect, this is easiest to do integrate, and with that coordinate transformation, as you saw, this whole thing just becomes gamma 0 sine theta, and we integrate from pi to 0. So this becomes a really simple integral. I'm just going to skip to the result here. It's rho v infinity gamma 0 span times pi over 4. So an elliptic lift distribution integrates really nicely. And let's now use the definition of our lift coefficient. So we can express this in terms of non-dimensional parameters here. So now I can solve for gamma 0 in terms of parameters that are perhaps more useful. And I get 2 v infinity, my wing or my reference area, lift coefficient, v over pi. Okay, so I could plug this into here, and I finally get that my, I didn't write this actually very well. Well, this is fine. Yeah, actually, this is fine. I'll write it this way. The tangent of my induced angle of attack, then, I'm just going to bring the tangent on the other side, is this thing here, which is going to be just CL over pi aspect ratio. So a lot of stuff cancels out. That's very nice. And aspect ratio, if you recall, is just span squared over area, or in other words, it's the ratio of span to a geometric chord. Okay, so I now have, for my expression of constant downwash, I have an expression for my induced angle of attack, which is also, by the way, constant, because if downwash is everywhere constant, induced angle of attack is just a ratio of that to v infinity with an arctangent, so that'll be constant. So my induced angle of attack is constant along the wing, and it's equal to CL over pi aspect ratio. All right, well, take this one more step into something even more useful. If we look at this figure here, right, this is a figure we saw before, v infinity, there's a downwash, and this gives us our definition of our induced angle of attack. This is how the attack is reduced. From Kajkowski, we would normally say if all we had was v infinity, we had this lift, but right, so the lift is equal to rho v gamma. But from Kajkowski, we could also take the cross product with w, and that would give us this drag component. So the drag here would be rho w times gamma. Right, so I do the cross product w cross gamma into the page, gives me a drag to the right. But what I notice here is if I draw my lift and my drag, right, so lift is perpendicular to this one, drag is in this direction, and the force that I get, if I want to consider, I could also do Kajkowski based on this resultant velocity vector. It gives me this force vector of which these two are components. This angle of attack, or sorry, this angle here is exactly the same as this angle here. So in other words, we can also say that the tangent of my induced angle of attack is my induced drag over my lift. Or in coefficient form, my induced drag coefficient over my lift coefficient. That's nice because now I can use this result here to relate my lift to my drag rather than just downwash and things that are less natural for me. I'm going to plug that in and I get what as follows. I get my induced drag coefficient equals, I'm going to take CL and multiply it on this side. So I'm going to get CL squared over pi aspect ratio. CL squared. All right, so this is a very useful result that we'll build on, and we'll see it will look very similar to this, that for an elliptic lift distribution, which for now, let's just say that's a pretty good approximation for the lift distribution of any aircraft. The induced drag coefficient we can get directly and very simply just from the lift coefficient and the aspect ratio of the wing. That's all we need to know, and I can compute my induced drag coefficient. We could also write this in terms of dimensional values, which is also very useful. So just expand the definition of the drag coefficient, lift coefficient, and I get that the induced drag is lift squared divided by dynamic pressure times pi times b squared. Right, so also an extremely useful result. Tells me I can compute my induced drag for this elliptically loaded wing. All I need to know is the lift, dynamic pressure 1/2 rho v squared, and my wingspan. All right, so that's two very useful results. This equation also tells me some fundamental things about what I want to do as an aircraft designer. I typically want to keep my induced drag low, right? I want to have low drag, and to reduce my induced drag, you can see there are two things that are going to have the biggest impact. It's not that I can just reduce the lift per se, right? I need my lift to balance my weight generally to keep me in equilibrium. But what I can do, in other words, is I can reduce my weight. So if I can build a lighter aircraft, I need less lift, and that can have a dramatic impact on my induced drag. So that's one reason why aircraft designers will go to great lengths, right, to truly try to reduce the weight of the airplane in order to reduce this induced drag term. The other we see is that wingspan has an important role. It's not really aspect ratio per se, that plays a role in the coefficient, but for the actual drag, what matters is not the aspect ratio, but the span. And so I'd like to have a really large wingspan in order to reduce induced drag. And this is why you'll see this both in airplanes and birds. If I'm a soaring bird that needs to travel long distances, I'd like to have very large wingspans to reduce this lift-dependent drag. Whereas if I was a hummingbird or a bird that needs to be really maneuverable, I'm really sacrificing, I'm taking a big hit here in exchange for high maneuverability. Same with airplanes. If I'm building a glider, it needs to go long range, be very efficient. I want it to be very light and have a very large wingspan. All right, two other quick things. I'll say it this way. Before, we saw for a 2D airfoil, right, CL was, let's say 2 pi, or more generically just M. Let's write M. Alpha minus alpha 0. But we found that that isn't going to quite work in 3D, right? Because now we've got this extra term, alpha I. So if we have a wing, let's just say the wing is everywhere, has the same airfoil, right? So alpha 0 is constant, lift curve slope is constant. Okay, we want to know how the lift curve slope changes. So for 2D, this is the lift curve slope, right? In other words, lift curve slope means how does my lift change with angle of attack? In other words, if I plot this alpha versus CL, much of it is linear, right? And then of course, viscous effects take over and I reach stall, but much of it follows this linear shape here. I want to know the slope, so that's the derivative of CL with respect to alpha. In 2D, it's simply M. But for a wing, I now have this term here, so I'm going to now write this as big CL. Let's say this is my big CL. How is it going to change? So let's imagine now that I've got my wing, so this is a capital CL. Because I've included now my induced angle of attack. Well, we saw already that for an elliptic lift distribution, at least, that this is equal to the arctangent of CL over pi aspect ratio. And if I assume a small angle, that induced angle of attack is small, which it generally will be, then I could approximate this as just CL over pi aspect ratio. Okay, and what I want to find now is this lift curve slope, but in 3D, right, I want to find what is dCL, capital CL d alpha. And it's not quite as simple as last time because while alpha only appears here, CL also appears here. So if I take the derivative of both sides with respect to alpha, I've got to do a little bit of algebra here. I'm going to kind of skip that, just do this in one step. It's fairly straightforward, but this is the result that I get. M divided by 1 plus M over pi aspect ratio. Now this is not an exact formula here because remember, one, we're using the formula for an elliptic lift distribution. Not every airplane is going to be exactly that. And two, we approximate it with a small angle approximation. But in effect, what this tells me is how my lift curve slope is going to change. So rather than have a slope of say M, which was, let's say before, let's say a slope of 2 pi, we'll say is M. Now my lift curve slope is going to be something less. And let's just put in a number to make this concrete. Let's say my aspect ratio is 8. So this would give me let's see, 2 pi divided by pi over 8, that's 1/4. 1 plus 1/4 is 5/4. So if I invert that, that's 4/5. So that's 80% of m, right? So my lift curve slope is going to be reduced by, let's say, 80% or whatever for an aspect ratio 8. And we can see that as the aspect ratio gets smaller, it's here in the denominator, this term is going to get big. This is the denominator of this whole expression. So my lift curve slope is going to get even smaller. As my aspect ratio gets bigger, right, if we go to the limit, the aspect ratio is infinite. This term is 0, so I have 1 plus 0 is 1. And my lift curve slope approaches 2 pi, my 2D result, which makes sense, right? As I have an infinite aspect ratio, my wing is infinitely long, and you know, I get 2D results. Okay, so that's one important thing. One thing that's really changed here, because of the presence of downwash, it's affected my angle of attack, which has introduced this new drag component of induced drag that we can now calculate, but it's also changed my lift curve slope. One last thing we're going to talk about today. Let's go back to that formula. So here is that formula, the fundamental equation. And what we see from this, well, let's say we want to create an elliptic lift distribution. For reasons we'll see next time, this is potentially a desirable shape to have. And so if we do that, we have to ask ourselves, well, how do we create that? We just assume that was the shape we have. Well, how do I actually make that happen? So if it was an elliptic, we saw that this downwash term here, this is just a constant. So that doesn't do anything, or at least doesn't give me any shape, because I want this to be elliptic. So we see that gamma, and typically I don't have any real control over V, right? It's just going to be V infinity. It in general does vary over the span, right? Because I may have a different wind speed over here as compared to here, either because of the wind or because I'm turning, doing a maneuver. So if I was doing this numerically, I'd want to include that. But as far as design goes, it's not really something I generally am going to be able to change. So if I want gamma to be elliptic, then if I move chord over to the other side, I see that this is going to be proportional to chord times the slope times alpha. Let me just forget about writing the y. Everywhere it's a function of y. So C, m, alpha minus alpha 0. Those are really the only things I can control. If I have the same airfoil everywhere and I twist it all the same, right? So if this airfoil is the same, what things are affected by the airfoil? Well, the airfoil affects my zero lift angle of attack and my slope, right? Because if this is my airfoil that I choose, this is alpha 0, and this is my slope. So when I choose the airfoil, I've fixed these. So if the airfoil is the same everywhere, those are everywhere constant. And if I have an untwisted wing, right, just same twist, angle of attack is going to be everywhere constant on the wing, right? I could pitch the whole thing up or turn and change my angle of attack, but it's everywhere constant. So if that is the case, then the only thing left for me to change is my chord. So if I wanted an elliptic lift distribution of lift, I'd have to have an elliptic lift distribution of chord. And the most famous example of that is the Spitfire. So if I look at the top view, which you can't exactly see, but if I was looking at the top view, oops, say here's the fuselage, right, the tail or whatever, the wing shape here would be that of an ellipse, right? So I could do that, right? And that elliptic chord distribution would give me an elliptic distribution of lift. Again, for now, we're just taking it that's a desirable shape. We'll see why it's desirable later, but that would be my only choice. However, I can change these other things. I don't have to assume they're constant. In particular, what I can change is the angle of attack everywhere on the wing, and I do that by twisting. And this is what's more typically done. Manufacturing a shape like this is much more work. I can then instead just have linearly varying wing shapes, right? This could be any shape, in fact, it doesn't really matter. And I can always twist the wing, right? Change the local angle of attack so that I can produce an elliptic lift distribution. So in other words, for any shape wing, I can retwist it to get an elliptic lift distribution. That doesn't mean that these are completely independent, right? The chord that I choose in the twist is going to have effects on my structure as well as sort of my stalling behavior and other things. So I do want to, as a designer, I do need to, there's additional considerations. But what this does mean is I'm free to choose different shapes. And in fact, this is what's normally done, right? Is that we have, well, for commercial airplane, probably another linear segment like this. So a linear block here and a linear block here. So I have more space here for landing gear, bigger chords at the root where I have more structural loading. And to increase lift where I lose something near the fuselage, but I don't create these complex curves generally because it's unnecessary, right? I can manufacture simple shapes that give me more or less what I want, and then add some twist to kind of fine tune the shape. All right, that's enough for today. So next time we'll take a more general approach and see why this elliptic lift distribution is a useful one.